So this is my last lecture. So in order to save some time, I already wrote down the summary of the last part of my talk yesterday. So yeah, we consider very general lattice model, many quantum many particle on lattice. Then I just assume that the particle number is conserved, and the system has lattice translation symmetry. Then you can define the unit cell. So in case of simple square lattice, the unit cell is just a single site. But in more general lattice, the unit cell may contain several sites. But anyway, so then under these conditions, we can define filling factor. That is number of particles per unit cell. And let's suppose that this filling factor is some rational number p over q. P and q are coprimes. Then, as I discussed yesterday, I want to consider some finite size system, but with the fixed filling factor, then gradually enlarge the system size. Then want to see what happens to the energy spectrum. And then the main observation is that I can do this flux insertion from zero flux to phi zero unit flux quantum. Then you have non-zero gauge field vector potential. But then I can apply the large gauge transformation. Then you come back to the original gauge with zero vector potential. But during this operation, the momentum of the system changes by 2 pi times nu times Ly. So if you choose Ly to be coprime with Q, then this is some non-trivial momentum change, which means that the final state must have the different momentum compared to the initial state. So if the system has a gap, then if you do this flux insertion adiabatically, you must follow the ground state. So you must end up with the ground state. But now the final state is different from the original state, which means that there must be degenerate multiple ground state. And because of this change of momentum, you can repeat this process many times. And you can find a new ground state up to q times. So for this filling factor, if the system has a gap, then there must be at least q-fold degenerate multiple ground state. And this is one kind of general version of Lipschutz-Mattis theorem, although there are many more generalizations these days, but this is one of the basic form of Lipschutz-Mattis theorem. But the theorem has an interesting history, so I just want to briefly mention the historical background. So as the name suggests, originally this theorem was presented by Lipschutz-Mattis paper. In, I think, 1961, something. But I think for a long time, this theorem received a few attentions, I think, because first in the original form, they just discussed a spin one-half chain at zero magnetization. So they show that this spin one-half translation invariant spin one-half chain at zero magnetization must be either gapless or has twofold ground state agency. That was a theorem. And apparently, the authors themselves didn't think this theorem too important because this paper is a kind of long paper published in Annals of Physics. But this now famous theorem was not even the main content, and it was put in Appendix B. And actually, I don't know how many people have actually read this paper, but I checked this paper, and in fact, there is a very interesting note at the end of the paper, or end of this Appendix B. So they wrote that, okay, so in this paper, they just discussed a spin one half chain. But then they announced that they will generalize this result to arbitrary spin quantum number, like 1, 2, 3, or 3 half, 5 half, 5 half, and so on. And they announced that the generalization to arbitrary spin quantum number will be published in subsequent publication, but it never appeared. And my guess is that as you probably know, that this theorem doesn't work for integer spin. So if you apply this theorem for integer spin chain at zero magnetization, then you don't have any constraint because integer spin chain at zero magnetization correspond to integer filling fraction in this language. So my suspicion is that initially they were too optimistic, but when they tried to write up, they realized that this theorem cannot be generalized to integer spin chain. And then maybe they gave up. But of course, that was related to the Haldane conjecture. So maybe they, they almost found a signature of Haldane gap. But anyway, they didn't go further. But then there's a famous Haldane conjecture. Although Haldane's original work did not directly discuss a Lipschutz-Mattis theorem, but he found a fundamental difference between integer spin chain and half-Order integer spin chains. And that was back in 81. Then after that, Affleck and Deep, Deep is same Deep, wrote a paper in 1985 or 6. And they just applied the same argument for general spin chain with arbitrary spin quantum number. So this shows that the spin S chain the translation invariant spin S chain must be either gapless or has doubly degenerate ground state at zero magnetization. So then they found a gapless or degenerate ground state only for spin half-Order integer. Of course, the spin 1/2 case was already known in the original paper, but yeah, here they clarified the fundamental difference between integer spin and half-Order integer spin in the context of this Lipschutz-Mattis theorem, which was consistent with Haldane conjecture. Yeah.
What was the method of proof in the original question?
Yeah, so they use a kind of variational argument, not this flux insertion. And yeah, they are kind of, yeah, maybe I will quickly review their original proof later, but yeah. Okay, then so I think so. Those are history background, and then I went to UBC as a postdoc with Ian Affleck, and we did the generalization. So we just generalize this to spin S chain at arbitrary magnetization. That was 97. My magnetization is then found that a similar constraint, this or degenerates. If this spin quantum number minus this magnetization is not integer. And yeah, funny thing is that at this point, I think we didn't invent anything technically new. So you can apply the same technique as in the original paper to this, just a generalized problem. And then show that when this S minus M is not integer, the system must be either gapless or ground state. You must have a ground state degeneracy. So yeah, technically we didn't invent anything basically, but I think physically this was maybe my most important contribution to this kind of subject, because so this condition looks strange, but you can always map quantum spin system to quantum many particle system, because for example, if you have spin S, then the smallest eigenvalue SZ is minus S. So you can associate this with a vacuum. Then when you increase SZ by 1, then you can identify this state as a single Magnus state or something. And so in this way, you can always map the quantum spin system to quantum many particle system. Then this mysterious number S minus M is nothing but, okay, so maybe this is opposite. So yeah, it's the same condition. So let's do the M plus S. Yeah, S minus M and S plus M, the same condition because 2S is integer. So if you do this, then this mysterious number S plus M is nothing but the number of Magnons per site. And then, so you can apply this deep Schultz-Mattis theorem not just for quantum spin system, but for more general many particle system, including fermion system. And moreover, in terms of this filling factor, this deep Schultz-Mattis theorem becomes more natural because this theorem tells you that if you have integer filling, you can realize a trivial state with a unique ground state with a gap. But if you have fractional filling, for example, if nu equals to 1/2, then it means that on average, every other site is occupied. So only half of the site is occupied by particle. And then you want to realize a gapped ground state, let's say. Then, of course, you can form this kind of ground state with particle occupied entity, occupied entity, occupied entity. And in terms of particle, this corresponds to a sort of charge density wave state. And if this particle were magnon, then this corresponds to Néel ordered state. But anyway, so if you can stabilize this kind of CDW state, then you can open the gap. But this CDW state breaks the translation symmetry. So if you realize this kind of ground state with a gap, then the ground state must be doubly degenerate, which is consistent with Lipschutz-Mattis theorem. And you can sort of intuitively understand that if you have fractional filling, and in order to open the gap and realize a stable ground state, you must somehow, you must have a degenerate ground state, at least in this example. But of course, this is just an example, so it's not quite trivial to say that you must always have ground state degeneracy when the gap is open, when this filling fraction is not an integer. But precisely this Lipschutz-Mattis theorem tells you that is the case. But in terms of this particle density or filling fraction, we can sort of naturally understand this Lipschutz-Mattis theorem. And actually, when I wrote this paper, yes, somebody came to me and asked if isn't this totally trivial? And yeah, maybe it is, but if that is a trivial, then you can go back to the Haldane conjecture. So the Haldane conjecture was initially very mysterious, and few people believe that. And you might have learned that this Haldane conjecture follows from the nonlinear sigma model mapping, and integer spin chain has effectively no topological term, and the half-odd integer spin chain has topological term. So because of this topological term, half-odd integer spin chain remains a gapless, but the integer spin chain has a gap. That's of course a very nice and interesting theory, but it sounds like a magic, you know. Why topological term makes this difference? But if you take this view, then integer spin chain, like a spin one chain, just correspond to integer filling. So number of magnons per unit cell is integer. So you can naturally expect the system opens a gap. But half-odd integer spin chain corresponds to fractional filling, like a 1/2. Then in order to open the gap, you must have a degenerate ground state. So in this view, it's kind of natural. So you might think it's trivial, but at least it wasn't trivial, you know, back then. So I think one of the nice thing about this Lipschutz-Mattis theorem was, yeah, in this way, we can sort of naturally, intuitively understand this mysterious Haldane conjecture, Haldane gap. Of course, that's not the end of the story, because as you know, this Haldane gap phase for spin one, actually odd integer spins, turned out to be a symmetry protected topological phase later. That's also a very interesting subject, but I'm not going to discuss SPT phase in this lecture. And this SPT nature is not clear from this Lipschutz-Mattis theorem because this theorem doesn't distinguish between really trivial phase and the SPT phase, but at least the presence of the gap for integer spin chain can be naturally understood by mapping the spin chain to a system of many particles. And Lipschutz-Mattis theorem is kind of very natural theorem in this view. And but I think the theorem is not totally trivial because as I mentioned, for example, this degeneracy could be the consequence of topological order, topological degeneracy. In that case, it's not so straightforward to understand the ground state degeneracy if that comes from topological degeneracy. But anyway, so this is a generalization. And then this was still based on original argument by Lipschutz-Mattis using some kind of variation argument, which has a difficulty when applied to two-dimensional or higher dimensional system. Although, well, yeah, you could argue that the original argument in some sense works for higher dimensional system, but there are some subtlety. And this flux insertion argument gives you maybe more, maybe perhaps better understanding of higher dimensional system. Okay. So, yeah.
So if you just have the Hamiltonian,
Mhm.
can you compute the mean, or do we have to have a?
Well, okay, so here I start from assuming the value of nu. But if you are in grand canonical ensemble, then nu is determined by minimizing the energy by changing nu as a parameter. So that has to be solved separately. Or in principle, you can, well, for example, in cold atom system, you can really fix the particle number. In that case, you can, give this nu as a condition. But in condensed matter system, usually this nu changes by getting some particle from particle burst or something. So in that case, you need to find which nu gives energy minimum. So then, okay, so I shouldn't spend too much time on this history stuff, but then this flux insertion and then more recently there are many generalizations as we already discussed, like generalization in the presence of crystal symmetries and discrete symmetry and so on, so on. So there are now maybe too many generalizations give you a complete list. But I want to also discuss different different application of this flux insertion argument. That is, this Lipschutz-Mattis tells you that if you have fractional filling, then the system must be either gapless or have a degenerate ground state below the gap. So if the system is gapless, then the Lipschutz-Mattis theorem says nothing about this gapless system, apparently. But actually, this flux insertion argument gives you certain momentum shift. So actually, it gives you some constraint even when the system is gapless. The Flux-Insertion. That is 0 to phi 0. Still, the argument I gave about the change of momentum is actually still valid for any system. So I didn't make any assumption other than this U1 symmetry and the translation symmetry to derive the momentum shift. So it should be also valid for gapless system. So you should have this. So this is still valid when system is gapless. Then what I can tell you is that usually you want to describe some complicated quantum many-body system using some low-energy effective theory. And if you have some low-energy effective theory, then your low-energy effective theory, okay, so you can ask, you do the same flux insertion process using your effective low-energy theory. And then, at least in principle, you should be able to compute the momentum gain of the system using the low-energy effective theory. Then the result must match this exact and rigorous result, because yeah, I didn't make any assumption to derive that result. So that must be always correct. So if there is a good. Then if you have your favorite low energy effective theory, you should compute the momentum shift to the in a response to the flux insertion, adiabatic flux insertion. So this delta px momentum shift obtained by effective theory must match that exact result, which was obtained without any approximation or assumption. And so this gives you some consent, because if you make some mistake, then you cannot reproduce this. Or if you thought you have effective theory for your system, but if that effective theory was wrong, then you cannot reproduce this result. And if your effective theory contains some parameter, then the parameter must be fixed so that it reproduces this result. So this gives you some constraint on effective theory. So this should apply to any possible low energy effective theory you might want to use. But I will discuss one particular example. That is so yeah, nowadays there are many low energy effective theory, especially field theory proposed to describe some low energy physics of quantum many-body problems. But maybe the oldest one, I'm not sure if it's really the oldest, but at least one of the oldest effective theory, low energy effective theory for quantum many-body system should be Landau's Fermi liquid. So this is an effective theory for interacting fermions. So interacting fermions are very difficult object because you have some fermion, like an electron, but this fermion interact with some other electron and are scattered off. So yeah, you need to take this scattering into account. But Landau says that at least in some class of interacting fermion systems, the low energy limit can be described in terms of quasi-particles, which behaves very similar to original fermion, but maybe effective mass is renormalized. And they do interact with each other, but in the low energy limit, there is no longer scattering. So each eigenstate, each plane wave state of quasi-particle becomes stable, at least in the neighborhood of Fermi surface. Quasi-particle. It's infinite lifetime. Yeah. So yeah, if you consider the momentum space, then there's some Fermi surface, and you can pretend like inside this Fermi surface, Fermi C, the quasi-particle is all the states are occupied by quasi-particles, and all the states outside Fermi C are unoccupied by quasi-particles. But as you know, actually these quasi-particles are only very defined concept near the Fermi surface. So deep inside the Fermi sea, the quasi-particle lifetime becomes short, so they are not necessarily well defined. But we can pretend like also deep inside the Fermi sea, all the single particle states are occupied by quasi-particles. So as long as you don't create a high energy excitation, the low energy excitations are exhausted by quasi-particle force states near the Fermi surface. So okay. Then, okay, so this Landau's Fermi-Lickit theory. So there can be density-density interaction between quasi-particles, but they don't cause scattering in the low energy limit. And then, so this Fermi-Lickit also have Fermi surface, and you can define Fermi C as a region inside the Fermi surface. But in general, the shape of the Fermi surface can be changed by interaction, at least in the lattice system. Okay, so in free space, the Fermi surface is usually sphere because of the rotation invariance. But on the lattice, there is no rotation invariance. So the Fermi surface takes some particular shape. And for free fermions, you can explicitly calculate the shape of the Fermi surface. But once you introduce the interaction, the Fermi surface, the shape can be modified by interaction. But then you can ask, so there's still a Fermi C for quasi-particles. And the shape is generally modified. But you can ask if the volume of the Fermi C for Fermi-Lickit can be modified by interaction. And this question can be answered using this kind of argument. That is, you place this Fermi-Lickit on torus or something, and then do this adiabatic insertion of AB flux, and ask how much momentum is gained by the system due to this flux insertion. And actually, this is kind of easy to calculate because if you insert a flux, every single particle state is shifted by momentum 2 pi over Lx to the right. So entire Fermi sea shifts by 2 pi over Lx. Each. So the total momentum gain is 2 pi over Lx times, so number of quasi-particle states inside the Fermi sea. That is proportional to volume of Fermi sea. But if you consider finite size system, the momentum is quantized in unit of 2 pi over Lx and Ly. So the so for two-dimensional system, for example, so the total momentum shift is calculated like this. And then you equate this with this one. So from this, actually, it's technically speaking, we need another step, but by comparing these two results, basically we can show that so Fermi sea volume is fixed to this filling factor mod modulo integer. And if you compute the Fermi sea volume for non-interacting Fermi gas, then of course you have this result. And so this can be integer, but this integer corresponds to number of completely filled bands. But anyway, so so for free fermions, we already know this relation. But once you assume that the low energy effective theory is given by Landau's Fermi liquid, and if there is no other low energy degree of freedom left, then all the momentum change should be produced by this shift of Fermi sea. So this relation must hold. And this suggests that, this implies that the volume of the Fermi sea is not renormalized by interaction. And this is actually one of the very classic, I mean, by classic, not non-quantum, but very old and well-known result, which is called the Luttinger theorem. So of course, this has been shown by Luttinger many, many years ago. But one of the advantages of this approach is that this argument can be applied to, in principle, to any low energy effective theory. So even for non-Fermi liquid, so my challenge is that if you have your favorite low energy effective theory, you should compute this momentum shift under adiabatic flux insertion, then get some result, and then compare with this exact result, and they must be consistent. Or if your theory contains some parameter, then this fixes the parameter. And in fact, there have been various discussions about modified version of this Luttinger theorem. Actually, one of them mentioned by Subir last week, I think. So if your system is not simple Fermi liquid, but something called FL star, then FL star has Fermi liquid like quasi-particle excitations. But other than quasi-particle excitations, there's a topological excitation, the Y zone in Z2 spin liquid. And if you do this flux insertion, you also create Y zone in addition to shifting the Fermi surface. And this Y zone creation absorbs a certain momentum correspond to filling factor 1/2. So the volume of the Fermi sea can be different from this standard one by 1/2 because this delta px momentum shift, part of the momentum shift can be carried by the creation of the visor. So yeah, that's just one example. So any low energy effective theory you might have, you can compute this momentum shift and compare with the exact result. That gives you some constraint. So this is a standard Luttinger theorem for Fermi liquid, but this can be also generalized to so-called FL star, so on. So then, well, yeah, I should say generalized. Then maybe I also want to make a brief comment about electron with spin and so on. So far for simplicity, I was discussing a spinless particle, so no internal degree of freedom. But in many applications, the electron has spin, or electron can occupy different orbitals and so on. So some extra internal degree of freedom. And yeah, you can also deal with those systems using a similar argument. For example, Spinful. And the typical model we consider for spinful electron is Hubbard model, for example. So for example, the hopping, so the upspin electron hops to neighboring site, preserving the spin. And for example, there's an on-site interaction between upspin electron and downspin electron. And you can also include more complicated interaction if you like. So in this system, okay, of course, in some applications, you also include a spin orbit interaction, then it's more complicated. But in this simpler version of Hubbard model, the number of upspin electrons and the downspin electrons are separately conserved. So in this case, you can define filling factor separately for up and down spins electrons. So for this, you can again do this flux insertion. But what kind of flux? That is a problem. So if you really imagine the physical flux insertion, then physical vector potential couples to charge. So the physical vector potential does not distinguish up and down spin electron. So yeah, if we consider physical flux or physical vector potential, so this couples charge. So if you insert a flux, then the system responds, and the upspin and downspin electron responds in the same way. So what matters here is the total filling fraction. And using this total filling fraction, total filling factor, you can apply Lipschutz-Mattis theorem or this Luttinger type theorem as you like. Yes.
So in the FL star state, to mention. So the Luttinger theorem would apply then to both species of quasiparticles, right? It's similar, but instead of up and down, you have lambda quasiparticles and the other.
Are you asking for FL star or?
Yeah.
Oh,
so if you have more than one species of quasiparticle,
yeah,
that's stuff. So the Luttinger theorem would apply to the Fermi volume of all your.
yeah, you can derive one such constraint, but later I will discuss a different constraint. But this can be, at least you can use this constraint. And so if you do this, then what you can say is that if this total filling is non-integer, then the system is either gapless or ground state is degenerate. And also, this is a bit of, I would say, overstretching, but if the system turns out to be gapless, then because this gapless excitation can be excited using this physical vector potential, which couples to the charge, then it is likely that this gapless excitation means some gapless charge excitation. Although, yeah, there are many subtleties about this, but and if there are gapless excitation which is related to some kind of charge degree of freedom, then the system is likely to be conductor. although this part is not quite rigorous, but I think it's natural to expect this. And in fact, if you have a Hubbard model and dope the system to make the filling factor to be some, incommensurate number, then your system is likely to be conductor because you can create a gapless excitation by applying the physical flux insertion or applying the electric field, in other words. But of course, sometimes this total filling factor can be integer. For example, we are often interested in so-called half-field case. This nu up and nu down are both 1/2. Then the total filling is 1, which is integer. Then if you use this insertion of physical flux or increasing the physical vector potential, then the momentum shift is now just an integer. So you cannot conclude anything using this argument. But even in this case, we can still use a flux insertion argument because I just need to introduce some flux in Gedanken experiment, or that is, I want to increase the vector potential in some way. But at least for this discussion, this vector potential doesn't have to be real one. I can introduce a fictitious vector potential as long as there is a conserved quantity. So in this case, as I mentioned, this upspin electron number and downspin electron number are separately conserved. So we can introduce fictitious vector potential. Which only couples to upspin electron. Yeah, of course, you can introduce vector potential which couples only to downspin electron, but let's also upspin electrons. Then you can still do this flux insertion process. Then what we can conclude is that if nu up is non-integer, then there is either gapless excitation or ground state degeneracy. And but in this case, the nature of the gapless excitation I cannot tell because this vector potential couples only to upspin electron means that by doing this flux insertion, you may be you may be creating a charge excitation or spin excitation or both mixed. and you don't know in general. This can be charge excitation or spin excitation, or both. So, but important thing is that even at half field, this nu up is 1/2. So this is not integer. So you can say that half field Hubbard model must have either gapless excitation or must have a ground state degeneracy. And in fact, we know that for in general, for attractive Hubbard model at a half filling, then these electrons form a singlet pair, but a singlet pair moves freely, so they condense as bosons. So you can have a kind of superfluid state, which is conducting. So in that case, you have gapless excitation, but no gapless spin excitation. But if the interaction is repulsive, then you can have Mott insulator. Then there is no low energy charge excitation, but there is low energy spin excitation. Or in 2 dimensions, you would have spontaneous symmetry breaking nail state, but still there are gapless spin excitation corresponding to Nambu-Gosson mode. And in 1D, there is no SSP, but for repulsive Hubbard model, you have gapless spin excitation, but no gapless charge excitation. But for attractive Hubbard model, at half filling, you have gapless charge excitation, but no gapless spin excitation. So it depends on the concrete model, but still, for this Hubbard type model at half field, if we use this fictitious vector potential, which couples only to up spin electron or down spin electron, we can restrict the possible phases which can be realized by this Hubbard type model. So yeah, whenever you have some conserved quantity, you can try using this kind of flux threading argument by introducing fictitious vector potential which couples to the one of the conserved charges. And now I'm really running out of time, but finally I want to briefly mention another application of flux insertion argument. That is, so far I have been discussing the momentum change induced by the flux insertion. But we can also ask how much energy is gained by system during the flux insertion. And so actually, maybe I didn't emphasize clearly, but this momentum shift, I gave you the exact number, but that doesn't depend on how fast you insert the flux. It just follows from the translation invariance and the large gauge transformation. So whether you insert this flux suddenly, very fast, or adiabatically, very, very slow, the momentum shift is the same. But on the other hand, if you insert a flux, you accelerate the particles, then the system, generally speaking, gains some energy. And this energy gain does depend on how fast you insert a flux. So depends on. the speed of flux. And it's generally not, of course, not quite easy to discuss very general case, but we can discuss a few very special limits. That is, first is instantaneous insertion. So that is okay. Well, this is a time, and I want to increase the vector potential from 0 to phi 0 or some particular value, let's say linearly. And let's say this final time is capital T. Then if you increase the flux in this way, then this corresponds to adding the, in terms of electric field is proportional to the derivative. So in terms of electric field, it's like a pulse of width T. And okay, so maybe I should have drawn this in the beginning, but instantaneous insertion means that you take the limit of this capital T goes to 0. Then, so this is, in this limit, this is a kind of quantum quench, you know. So up to time 0, you had 0 vector potential. But after T equals 0, you suddenly switch the vector potential, switch on the vector potential. So it's kind of, it's a special case of quantum quench. So quantum quench. So the energy gain of the system is given by the expectation value of Hamiltonian with some vector potential. So yeah, let's say this is vector potential in x direction. And let's denote this final value of vector potential as calligraphic A. Then in case of quantum quench, the wave function cannot follow the evolution of Hamiltonian because there is no time. So the energy expectation value after the insertion of the flux is just given by expectation value of the new Hamiltonian, including the vector potential with respect to the same ground state, original ground state. And then you subtract the energy expectation value of the for the same state, but with 0 vector potential Hamiltonian. So this is the energy gain. And you can, if you like, you can expand this energy gain in terms of the final value of the vector potential, capital A. But then the question is, what is the physical interest of this energy gain? And in fact, I can argue that this is pretty important because because if you consider Hamiltonian in the presence of vector potential, if you take a derivative of Hamiltonian by vector potential, then you obtain a current density operator. So the current of the system is maybe 1 over volume of the system. And then you take a derivative of Hamiltonian by. So this is a current operator. So that means that, okay, so this is not exactly the same as this energy gain, but you can write down the formula for the current expectation value after this flux insertion process. After flux insertion. As the similar quantity like that is take the derivative of Hamiltonian by vector potential, and after taking the derivative, you set the value of vector potential to be final value of the vector potential. So this is a value of the current expectation value after the sudden flux insertion. On the other hand, you can formulate the this current in terms of the response to the electric field. So this current at time t would be given by sum over nth order contribution, and nth order contribution would be given by nth order conductivity. And okay, so this is a response function. Okay, so yeah, I need an integral. 0 to t, 0 to t. So yeah, I'm including all the nonlinear responses to the electric field, of course, starting from the linear response. And at each order, there is some response function. And you have some delayed effect of electric field at time t1 and time t2, and so on. So this is a current as a response to the electric field, and n equals 1 gives you linear response, and n equals 2 second order response, and so on. So in principle, you can expect this. And then here I consider the sudden insertion limit. That is, I take this t to 0, and then this electric field becomes infinity because pulse width becomes narrower and narrower. So it's like a delta function. So in that limit, I can easily calculate this because basically you can replace this response function at a 0 delay time. So in the sudden insertion limit, this sigma n can be replaced by 0 delay time response function. And then you can integrate over this electric field. And if you integrate over each electric field, you just get the vector potential, the final value of vector potential. So J of t equals to t becomes summation over n and sigma n at instantaneous response. And then a to power of n. So this shows instantaneous nth order response. So you can compare this expansion with this expansion, and you can try to expand this. You can do the Taylor expansion of this HA. Then you can find that this instantaneous response is given by the so sigma n is given by the ground state expectation value of n plus first order derivative of vector potential and set a equals to 0. So this is a formula constraining the nth order instantaneous response. But this response function I have defined in terms of the real time. So maybe you are more familiar with discussing the conductivity in frequency space. So in terms of frequency space, this is corresponds to the frequency integral. There's some prefactor, but so now this is nth order conductivity as a function of frequencies. So this tells you that nth order nonlinear, okay, so if for n equals 1, this is a linear conductivity, but for general n, this is a nonlinear AC conductivity as a function of n frequencies. And if you integrate over all the frequencies, then this corresponds to instantaneous nth order response, which is given by this simple expectation value. And this is valid for any Hamiltonian. And of course, for linear order n equals 1, this is very well known so-called F sum rule, frequency sum rule, which gives you this integral by second order derivative of Hamiltonian with respect to vector potential. But for higher order, it is given by very similar formula. So okay, so yeah, I already going over time. So this is another application of flux insertion argument, although to derive this, we haven't really used large gauge transformation. So for this argument, you don't have to really insert a unit flux quantum, but it is also interesting to compare this with this Lipschutz-Mattis type business. And also I wanted to discuss more detail, but yeah, one of you asked about the original proof of Lipschutz-Mattis theorem. And in the original proof of Lipschutz-Mattis theorem, they just constructed the variational state by applying this operator ux to the ground state. Although they didn't discuss any gauge transformation or anything, but their variation state is same as the large gauge transformation of the original ground state. And the physical meaning of Lipschutz-Mattis original variation state is nothing but you start from the ground state and then insert a unit flux quantum suddenly, not adiabatically. So after suddenly inserting the flux, then the momentum shift is the same. So momentum changes from the original ground state. But because you suddenly inserted the flux, in general, you can create excitations. And in fact, in higher dimensions, this variation state can have very high energy. But in one dimension, you can show that this post-quench state has a low energy, only order of 1 over L compared to the ground state. So you can use that as a variation state. And that was how Lipschutz-Mattis proved their original version of the theorem. But same state can have also interpretation as a post-quench state after the sudden flux insertion. And if you consider this energy expectation value for this post-quench state, you can also derive this F-sum rule, frequency sum rule, including nonlinear conductivity ones. And on the other hand, if you insert the flux adiabatically very slowly, you can derive very similar formula, but very different but similar formula, which gives you the nonlinear version of the Kohn formula, which determines the nonlinear Drude-Waits. So this is very simple physical process, but yeah, somehow we can use this flux insertion argument to derive many different results. So I stop here. Thank you for your attention.
Okay, we're a bit over time, but let me see if there's any quick question. Yeah.
About the proof of Luttinger's theorem, did the single particle states also include states deep inside the VC? When we calculated the momentum shift in the low energy theory, are we also including particles deep inside the VC?
Okay, so yeah, that's one of the frequently asked questions. But so when you insert a flux in Fermi liquid, only changes occur near the Fermi surface. So you can just count the changes near the Fermi surface. So it's perfectly legal. But this counting, same result can be obtained by pretending as if all the states inside the Fermi surface, including the deep inside Fermi sea, each state is occupied by quasi-particle, which is not physically correct, but because they don't change by this shift. So yeah, that's kind of fictitious assumption, but because those deep inside the Fermi sea state don't change at all, it does give correct counting. So if you are afraid, you can forget about the deep inside the Fermi sea state and just count new quasi-particle occupied state and a new quasi-Hall state, and the result is the same.
All right, I think we should move on to the break and then come back for the next talk at 11. So let's thank Masaki again for